All right, today we're going to continue looking at lighting branch circuits. Of course, as always, we start with the objectives. So this is what we want to take away from this. We're going to learn some more terminology, as it turns out today, with this. So hopefully by the end of this PowerPoint, you'll understand what general lighting is, accent lighting, task lighting, and security lighting. So those are the four big categories of lighting. You may recall having me mentioned a couple of them already. Also, estimating loads for the outlets connected to a branch circuit, determining how many receptacles connect to a branch circuit. So these are all important things as well. Our objectives of also learning how to draw a cable layout, wiring diagrams for branch circuits, something that's we need to do, need to be able to do, I should say. So we have that as well. Also, properly sizing outlet boxes based on the number of conductors and devices. All right, and then of course the NEC. You know, we everything we do revolves around the NEC, right? We have to make sure that we should be able to explain the requirements for luminaires in closed closets. I actually went over that in a previous PowerPoint, so we'll touch base on it again, but hopefully you should be able to explain that when we're all said and done. So as I just said a moment ago, we could categorize lighting into four groups. General lighting, so your general overhead lighting that you would use to light rooms and so forth. Accent lighting. Accent lighting would be used to focus attention on certain things, maybe a feature wall or artwork or something of that nature. Light that's going to be pointed in a directional lighting. Then we have task lighting. You're going to see task lighting places like kitchens where you have counters, maybe in workshops, or if you have a workbench, that's where you're going to see task lighting. And then, of course, security lighting, outdoor lighting. Usually, those are your lights that are going to be on photo eyes or timers or things of that nature. The American Lighting Association offers excellent residential lighting recommendations. Again, recommendations, not to be confused with the NEC recommendations. All right. So laying out general purpose lighting and receptacle circuits. Well, let's take a look at this for a second. This is our job as an electrician to do this, doing the layout. That's, so we have to consider certain things. We're going to take a look at this. General purpose receptacles and lighting outlets with more than one circuit. So receptacles and general lighting tend to get lumped together. You'll see this later on when we get into doing load calculations. When we do a general lighting load, for instance, the receptacles are included in that. And the reason being is because we're plugging lamps and things into the lighting, the convenience outlets, so they kind of lump together. So we're talking about general purpose receptacles and lighting outlets with more than one circuit. Yeah, nowadays in a typical house, we'll probably have more than one lighting circuit. Back in the early days, you might have only had one circuit for lighting and receptacles and so forth. So, but we have to look at something like that. Separate general purpose receptacles and lighting outlets. So lighting outlets will tend to be up on the ceiling or maybe on the walls. And then, of course, we have what we call our general purpose receptacles that must be installed, that are required in a dwelling. It says economize, talks about economize on wiring materials by connecting receptacle outlets back to back. Well, that's referring to when we do our rough-in. we want to keep our wiring economical. We don't want to waste. We don't have a lot of waste, so we want to, daisy chain our receptacles together. We're talking back to back. If, for instance, if you have receptacles on opposing walls, you have adjoining rooms. We're going to connect the receptacles, daisy chain them together. So you may have receptacles in adjoining rooms that are on the same circuit. We're basically piggybacking them. That's what they're referring to. Running a branch circuit first to the switch, then to the controlled lighting outlet. So that's a pretty common. It's a pretty common technique in residential that we would take our home run. Of course, we know what the home run is, right? That's the branch circuit wiring that comes from the panel to our first device. So a lot of times what we'll do is we'll just run it right to the switch. That's where the home run is going to come to, and then we're going to go up to the lighting outlet with our switch loop or our switch leg. Installing a receptacle below the room wall switch. That would be, you get switched outlets, especially, still a pretty common thing for living rooms and bedrooms to have switched receptacles. That's where you would get into the split receptacles and things of that nature that we've talked about. And the other thing that's very important now, consideration of furniture placement. So when you look at a room, like you look at the layout of a living room, for instance, you should have a pretty good idea where they're probably going to want to put a couch and and sitting furniture. You don't want receptacles to be hidden behind furniture, so you want to think of things like that. Older houses, I have one in particular where it just seems like most of my receptacles are hidden behind furniture, and it's just the way the rooms are laid out dictates a lot of times where the furniture is going to go. So we have to give consideration to that, where furniture might go, so that we have outlets that aren't buried as well. And in fact, in older houses, it's more of an issue because back you go back 50 years ago, 60, 70 years ago, they didn't have the provision in the code book that said we had to have so many outlets per wall space. So if they had one outlet on a wall in a bedroom, and that's right where the bed's going to go, now you got an outlet that's behind the bed. It's kind of a pain in the neck. So that's why the code has changed over time and make it so that we shouldn't have to bury outlets behind furniture. But we know it's something we still have to think about. Maximum number of receptacles on a circuit or lighting outlet. Now this is an interesting thing. We'll talk about this for a second. So the National Electric Code does not specifically tell us how many receptacles we can have on a circuit. Theoretically, we could have as many outlets as we want on a circuit, believe it or not, especially because we're talking general purpose outlets or lighting outlets. However, we see that for the new people, you see the term for dwellings. Just so you know, again, this is another one of those NEC terms that's going to come up again, and again. They don't talk about, you'll never usually see things like houses mentioned or residential. They'll call it dwelling unit. So what we might consider a residential, a residential occupancy, they call it a dwelling unit. Basically what that means is it's a place where someone's going to live. It's going to have bedrooms, it's going to have a kitchen, it's going to have bathrooms. And they distinguish non-dwelling units versus dwelling units. That's how the code describes it. However, so in a dwelling unit or a house or a residence, we're not allowed to load a circuit to more than 80% of its rating. So what that means, guys, is if you have a 20 amp circuit, we're not allowed to load it up to more than 16 amps or 80%. If it's a 15 amp circuit, it'll be 12 amps. So we have to consider that. Now, the way it works out, the way the calculations are made, a receptacle outlet is based on what we call 180 volt amps per outlet, or 1.5 amps per outlet. So if you take, for instance, a 20 amp circuit and divide it by 1.5, it comes out to like 13.3333. So they've determined that the recommendation is a maximum of 13 receptacles on a 20 amp circuit. And that's where that comes from. It's based on 1.5 amps per receptacle, or 180 volt amps per receptacle. So they've rounded it off to 13 receptacles is the recommendation. It's not a rule, it's a recommendation. And then on a 15 amp circuit, same thing. You take the 15 amps, you divide it by 1.5, and it comes out to, like, I think 10 amps, or excuse me, 10 receptacles per 15 amp circuit. That's the recommendation. I would say on average, it's hard to say, but we probably put maybe 7 or 8 per circuit. We try to keep it to like 7 or 8 outlets per circuit. But we could go, recommendation wise, with quotations, we could go up to 13 on a 20 or 10 on a 15. Okay. What else do we have to think about? So there it is right there. Depending on the expected connector loads, approximately 10 to 15 outlets per circuit can be included. They're saying, in the PowerPoint it says 10 to 15, but it's really 10 to 13. But again, it's not a rule, just good practice. Some things are rules and some things are good practices. Article 210 in the NEC requires that loads be divided evenly among circuits. So we have to consider that as well. On a typical residential service, for instance, you have a 240 service coming in. That means you have 2 bus bars. That means every other breaker in that panel is going to be on the opposite leg coming in, right? So we want to evenly distribute the load between the 2 legs coming in. We don't want the majority of the current being drawn on one leg of the service. So we got to consider that too. These are all things as electricians we have to think about. All right, let's take a look here, guys. Some symbols. First, starting from the top left here, you got the duplex grounding type. See, you got the 3 prongs on there. Somewhere about 1996, the code made that a requirement that all receptacles had to be grounding type. It was 96, I say thereabouts. It was 96. Now, you will still come across receptacles that are not grounding. That happens. I mean, because obviously houses are grandfathered in if they were built before 96. So there's one of 2 ways. Like if you have to go into a house and replace receptacles or add receptacles, a couple things you can do. You can get replacement receptacles that are non-grounding type, or you could install grounding type receptacles, but you have to label them and say that there is no grounding conductor. It's supposed to be labeled on there. Or the other thing is you could add a grounding means, which is probably the most difficult part, probably the most difficult thing to do. So you're probably better off just labeling it as not, no ground, no equipment ground, basically is what it says. No equipment ground, or put in the old replacement non-grounding type plugs. So that's perfectly acceptable because it's grandfathered in. Then you get your split wire type receptacles. This is what we're talking about, where you have your half of it is switched and half of it is constant power. So you see that on this particular one, you see they show 2 terminals on the one side and 1 terminal on the other side. So you'll have a common neutral on one side, and you have your switched and your constant power terminals on the left side. Everybody see that? Then you see a terminal, a symbol for the ceiling wall outlet. And you see the little circles on either side. You see the one on the right side is more of a golden color, and the one on the other side is a lighter color. Just for affiliation, guys, if you're looking at a receptacle or a switch or a lamp holder, the brassy or the more golden color terminal is going to be for your hot, and the silver or the lighter color terminal is going to be for your neutral. Just remember that. So you see that common here again, pilot light, you see the same thing. With on the left, you see the silvery or the lighter color, and you see the yellowy or brassy color is going to be on the right. That's your hot. So moving back to the left bottom, you have your single pole switch symbol, standard symbol for a single pole switch. And then in the middle, you have the three-way switch. You see you have the common terminal on the bottom, and then the two upper terminals are your travelers, and you basically toggle between. And then, of course, last but not least, the four-way switch. Four-way switch is used in a situation where you're controlling lighting from more than two locations. And basically, you have travelers coming in, travelers going out. And it toggles between the sets of travelers. We'll get into that more extensively when we start talking about four-way switching. Drawing a cable layout and wiring diagram. Typical house plans show the electrical symbols on the construction floor plans. One thing I will tell you guys is, well, first of all, we'll be getting into, we're actually going to be doing blueprints in this term. You're not going to see electrical plans for houses, for residential dwelling units that often. Oftentimes, when we go into a house and do a rough-in, do the electrical installation, we're going to be working off of basically the code requirements and or the homeowner or the customer. They may have specific things that they want, or whoever we're working for. It could be a general contractor who's building a series of houses. So we don't rely on plans as much with dwelling units, just so you know. It's more, you're going to see that a lot more in commercial. But it says rarely are separate electrical plans provided. So that's true. So if you do happen to have plans for a residential dwelling, they're probably not going to have separate plans. When you get into commercial, it gets much more complex, much more layers to the electrical, or well, not electrical, but just the drawings in general. You're going to have electrical, you're going to have architectural, you're going to have mechanical, site plans, plot plans, what they call elevations. You're not going to have all that with residential. You might have one drawing that has everything on it. And as I said before, you may only get something that has locations and very little detail. It's going to come down to the customer, what they want. We might need a list of equipment that's going to be installed, like ranges, dishwashers, and things like that nature. And that's going to really dictate a lot of our what we're going to be installing as well. Here we go, guys. Here's a look at a drawing. You see down in the bottom left there, right over here, you see the lighting panel. And we see coming out of there is a home run going up to the first receptacle. And it looks like 2-wire. And then from 2-wire going down here to this receptacle. And then we got 2-wire going over to a third receptacle. Then we're feeding a 3-way switch. You see that, guys? You see between the 3-way switches, we got the 2 hash marks and the half a hash mark. That indicates that we have a 3-wire. So we have a 3-wire connection going between our 3-way switches. And then lastly, we have a 2-wire going up to our light in the center of the room. Everybody see that? So that's how we determine, in this particular drawing, it's telling us, it's showing us what cabling we need. Now, I would hope that, you guys should be able to figure out, if you see 3-way switches, it should click in your mind, okay, I need 3-wire between them. It's important information because if, let's just say, for instance, you were pricing out a job for somebody and you don't catch that, you see 3-way switches, but it doesn't click in your mind, oh, I need 3-wire. And then, so you give them a price on the job. And then later on down the road, after you've already given them the price, then you realize, oh no, I need all this 3-wire. That's a big miss on something like that, because I'm going to tell you right now, the biggest cost, the two biggest costs on any electrical job is going to be labor and wire or copper. So if you miss, especially on a larger job, if you make a lot of mistakes on things like the difference between 2-wire and 3-wire, that's a big financial hit right there. And you're probably going to have to eat it. If you've given them a price on the job, you've already settled on a price, and then all of a sudden you realize you screwed up on your estimate. Now you're eating that cost. So if you're trying to make money, those are things that we have to pay attention to. Things like that. Those are little details, but boy, they can cost you if you're doing bidding work. All right, let's take a look here, guys. This is a good illustration. All right, so first of all, I want to start here on the left side of this drawing down here. This little symbol with the curved line, the little curve, and the two little terminals, that's your breaker. That's a symbol, universal symbol for a breaker. And then to the left of that, you see this line on the outside. That's our neutral connection. So you see the neutral connection going along, basically in and out of each device. And then this is a line diagram, by the way, guys. And then we see from the breaker, we're hitting each device, right, on the other opposite side. Then we're going into a switch box. See that? We look here in the middle, we're right here. If I could get it to stay zoomed, it's kind of hard. Stay zoomed there. Come on. So you see this? These little dashed lines indicate the boxes, the switch boxes. So we see that we had the power. Let's look at this first now, guys. We see the neutral connection. Remember, we don't connect neutrals to switches. You see that? It's a splice right there, typical splice. So the neutral's just splicing right through. Ultimately, the neutral is going to go right to the lighting fixture. Now, see this where it says traveler conductors? This is where the 3-way or the 3-wire switch comes into play, or the 3-wire conductor, the 3-wire cable. So you need black, you see black and red, and then you also have to consider the fact there's a neutral there. So we need a 3-wire between our 3-way switches. Now, on the bottom here, guys, you see it has the arrows pointing to 3-way switches. That's what we call our common connection. So on the left 3-way switch, we're coming into the common with power, right? And then if you go over to the other switch on the right side, from that common, see that's connecting right to the light fixture? So that's the deal with 3-way switches. Power is either going to be coming in or going out. So on our first 3-way switch, we got power coming into the common. The travelers are basically carrying your circuit. And then coming out of the common on the right-hand side here, that's feeding up to our light. That's a real excellent wiring diagram. I like that one. That shows you exactly how a 3-way switch works, or how it's wired electrically. Everybody see that? Good. That's a good illustration. 15-amp branch circuits. So typically, guys, your general purpose receptacles in a dwelling unit are going to be 15 amp. So, there's other specific circuits in a house that are required to be 20 amp. But your general purpose receptacles are going to be 15. Article 210, GFCI Protection for the receptacles located outside the front of the house. So by code, the NEC does require that we have outdoor receptacles on the front and the back of our house. And they need to be GFCI protected. AFCI protection. So receptacles inside your house. Article 210 list all the locations that AFCI protection is, pretty much all the receptacles in a house at this point need to be AFCI protected. Whether it's living room, bedroom, dining rooms, sunrooms, even kitchen receptacles, all have to be AFCI protected. Now, there are some that are required to be GFCI protected as well. But with few exceptions. If you visit Article 210 and look at the requirements, you'll see that the vast majority of all the receptacles in a house need AFCI protection. 404 talks about neutrals at a switch location. So I just want to really quick jump over here into the National Electric Code. And there's even a note here that talks about it. Why we have to have neutrals at switch locations. So occupancy sensors, we look at this note here. Occupancy sensors are permitted to control lighting outlets in lieu of wall switches. One of two requirements must be met in order to use occupancy sensors. Either a regular wall switch must be present in addition to the sensor, or the sensor must be equipped with a manual override that allows the sensor to function as a switch. Either type of wall switch can be located in a customary location. Now, this is the reason why we need neutrals at switch locations, because now people are using occupancy sensors. So back in the day, when electricians first started putting these things in, they were, they were like connecting to the grounding conductor and things like that, which is a hazardous situation, because now you're using a grounding conductor as a return on a circuit. So now you're putting a current on a ground conductor. That's not a very good thing to do. It's a hazardous thing to do. So the NEC added that a few code cycles ago, that we have to have neutrals at switch locations for occupancy sensors. But what they're saying, if we have an occupancy sensor, it can't be the sole means to turn that light on and off. You need to either have an additional manual switch or some sort of override, which if you look at occupancy sensors, if you buy one, you'll see that they actually have a switch where you can turn them on and off on there as well. Let me just go into the code book here for a second. I got a picture here. I just want to show you guys this. It says here, the grounded conductor. So we know, guys, that the grounded conductor is the neutral, right? That's the other name for a neutral. Shall be extended to any switch locations necessary and shall be connected to a switching device that requires line to neutral voltage. That would be an occupancy sensor. To operate the electronics of the switch in a standby mode and shall meet the requirements of 404.202.c. So I recommend you visit Article 404, switches. That's on page, for some reason, that's all kind of blurred out down there. I don't know why, what the number is. But Article 404 covers this stuff. Even talks about grounding conductor switches at circuit breaker shall not disconnect the grounding conductor of a circuit. Of course, I talked about that before, that we don't switch neutrals. So that's an important thing, but I recommend you review that. All right. Back into the PowerPoint. All right. Not loading up here. All right. Where did my PowerPoint go? Get this to load up. Bear with me for a second, guys. So yeah, so we have to have the switches, and also, guys, that neutral has to be at least at one location in a room. So if you have more than one switch location in a room, it's it's required to be at least one of those locations. It doesn't necessarily have to be at multiple locations. As long as you have a neutral present in that room, in one of the switch locations. That's the other thing as well. All right, let's take a look here, guys. What do we got going on here? Hopefully you guys recognize this. We see these symbols here for the receptacles. You guys see that they're half shaded. That would be indicative of a switched receptacle, wouldn't it? Or really a split receptacle. You see half of it shaded and half of it isn't. And you notice how we have, once again, 3-wire going between them. So let's just take a look. See this here, guys? This is the home run going back to the panel. This is A16. So that would be the A phase, and that would be breaker 16. We got a 2-wire coming into our first receptacle, and coming out of that receptacle to a single pole switch and then up to a light. And then also coming out of this receptacle, we're hitting another receptacle. Also, we're hitting a weatherproof GFCI outside, right? That's on the outside of the house. We're going to continue over. We're daisy chaining these receptacles together. Then we're bringing power to a switch over here. That's going to be the switch for your receptacles. Everybody see that? So this switch is controlling your receptacles. Then we're coming out of this switch. We're bringing power into a 2-gang switch on this wall. You see the F? That indicates that's for the fan. And the other switch would be for your light. Everybody see that? So that's how you would do that layout if you were drawing in your sketch drawing for your circuit layout. Fairly simple drawing, but it kind of shows you what's going on. Hopefully everybody recognizes that and sees that, what's going on there. All right. Determining the sizes of boxes and conduit bodies. Some of you guys just last term did box fill and conduit sizing. 2 different methods. If it's for this purpose, we're going to talk. We're kind of concentrating on residential. So we're using nail-on boxes probably. Nail-on boxes will actually have that information stamped right in there. It'll tell us how many cables we can get in, and so forth. However, we would have to, again, refer to the NEC for this information for sizing boxes. 314, Article 314, I believe it is, we'd have to go to for box sizing. One of the things we don't want to do is jam wires into electrical boxes. You got to be very careful that. For you guys may have even had this experience in lab. Particularly with residential, you have that bare conductor, that grounding conductor, that could be a real problem in a box. When we start jamming wires in there, lends itself to shorts. So the ideal situation, guys, is to use the deepest box we can install. The more room, the better. There's no reason to skimp on a box. There's no reason to use a shallow box if it's not necessary. The deepest box we can install is probably the way to go. You're going to really appreciate that when it's time to put your devices in and so forth. It's worth it to pay the extra price for the larger box in the long run. It's going to cause less problems for troubleshooting, and all that. The only time you're going to go with shallower boxes is out of necessity. You just can't seem to get the bigger box in there. So that's what you want to do. Secondly, pigtails connected to the receptacles need not be counted. So if we're sizing our box, some of you guys might remind us, we have to account for every conductor that comes into that box when we're sizing it. I'm not going to go into a great bit of detail because we will be covering this later on down the road. Like I say, some of you guys just had this recently. But there's an allowance for each conductor that's coming into that box. Article 310, 14, 16. There's tables A and B. We go to those tables. Each conductor, whether it's a 14 or a 12 or a 10, has a certain cubic inch allowance. The device itself has an allowance. that we have to factor in when we're sizing the box. The box itself has a cubic inch rating that shows how much internal space it has available. So pigtails, we know what pigtails are, right? That connection that comes from the wire nut to the device. We don't need to count those conductors, so we only count the conductors that are coming in and out of the box for sizing purposes. So as they say, a conductor, no part of which leaves the box, shall not be counted. However, guys, as just previously stated, the larger the box, the better. Those tables just essentially show us the minimum size boxes we can use. So if you're using table 31016A and table 31016B to size your boxes, remember that, guys. If you find it in the code, okay, I can use this size box, a 4-inch square by 2 1/8 inch deep with a 1/2 inch mud ring. That's the minimum size. If you can get a bigger box in there, be my guest. Grounding. Metal boxes have to be grounded. We've talked about that. Anything that's potentially metal, any metal that's potentially current carrying has to be grounded or bonded, right? Equipment grounding conductors, and the cable is connected to the metal box. In a non-metallic box, we go right to the green screw on the device, right? But we also have to bond our grounding conductors together, right? We have to either use one of those little barrel crimps or maybe a greenie. For you guys that are not familiar with greenies, that's that device that looks a lot like a wire nut, except it's got the little hole in the top. Those are usually used when you have one device in the box, though. As we said before, bedrooms are going to typically have the split wire or the half switch receptacle we talked about before. Usually it's going to be the top receptacle that's going to be, in this case, they're saying the hot. I don't know. To me, I think I'd rather have the top one be the switch one, but you got to be careful, especially if you're plugging in things like alarm clocks. Make sure you don't plug it into the part that's switched, because you'll screw up your alarm clock if you if you do that. They're saying it's recommended the bottom portion be switch controlled. I guess so. I guess it makes sense, because when you're naturally reaching down to plug into a wall receptacle, your natural tendency is going to be to want to plug into the top one. So whatever devices are going to be, like your clocks and things like that, you're going to want them to be. I don't know. That doesn't make sense to me. I always thought that it should be the top one, but okay, whatever. I would want to have my stuff that I'm not unplugging all the time in the bottom plug, and the top one is the one I'm normally going to reach. But to each his own, I guess. Split wire receptacles are horizontally mounted. The switch portion to the right. So if you have horizontal, you should stay to the right, I guess, on that one. I don't know how many you're gonna horizontal ones you're gonna find, but you may occasionally find them that way. Baseboard heating. So some of us may have electric furnaces, forced air, wall-mounted heaters, baseboard heat. Typically, that's going to be hardwired. Heat pumps, resistance heat cables. Some of you guys might have, if you come across heated floors. Let's see how far. Okay, just trying to get an idea here. Believe it or not, when it comes to closed closets, Article 210 does not require that closets have lights in them. However, there are local codes and there's local jurisdictions, and like for instance in Massachusetts we have the Mass Amendments. So various localities may have their own say on that. So we have to check. Maybe they do require them, but the NEC does not. Obviously, you have the potential for fire hazards when you're storing materials, clothing in closets. So that's something we have to consider. That's why there's these provisions that we have with lighting. We don't want to have hot lights touching potentially flammable material. You guys might recognize this illustration. I went over it in a previous PowerPoint about what is considered closet space or storage space. Again, typically looking from the front view here, it's from the rod to the floor, and then we typically have that shelf, and from the shelf to the ceiling, and it's going to be at least 12 inches from the back wall out, or the width of the shelf. And as far as the lower portion, the B portion, you look over here to this, it's going to be the width of it's going to be at least 24 inches in width down to the floor. And basically to the bottom of the shelf, I guess, really, is considered your storage space. So the gray area is considered non-storage space. So our lighting can be in that area on the wall, above the door, or up in the ceiling area. And we touched base a little bit about this, what's permitted and what's not permitted. So I'm not going to go too crazy talking about that. Again, you can review this. You see what's permitted and what's not there. And again, we also see where the storage space is, and we see the requirements. Again, not to be redundant, because I did cover this in a previous PowerPoint, but there you go, folks. All right. Again, if you have any questions about any of this, it's kind of hard to cover every single little aspect of any of this stuff. So if you have any questions, you can always email me. I will see you guys on the next one.